Hi everybody, we're going to section 3.3. We're going to do a bunch of integral problems, show you how to do them really good, and we're going to show you some rules. We've kind of been using these rules already. Now I'm gonna present them more just formally, so you got them, and that'll be a good thing. Okay, so let me just switch cameras, and I'm gonna start some math. We want to start with this problem right here. We want to find the integral of 3x squared, 3x to the seventh minus 15 square root of x plus 14 over x squared. I've noticed that when I was in school, we used to always call they always call square root of x. Now students tend to call it radical x, but it means the same thing. Um, and if you notice, there's no limits of integration here, which means that I'm not looking for a number. I'm looking for a function. I want to find the antiderivative, and that's exactly what I'm going to do. And I'm going to do it the way we've been trained to do it. So first thing I'm going to do to make it actually easier is I'm going to rewrite this so it's completely in terms of exponents because square roots and this, I'm going to rewrite it as follows. So I want to find, so this is all equal to the integral of, well, 3x to the seventh. I don't have to do anything. That's good already. Now, instead of writing square root of x, I'm going to write x to the 1/2 power. Because again, with calculus, it's much easier if you put things in terms of exponents rather than have radicals. Plus 14 times x to the negative 2 power dx. Now, this is going to be just basically the power rule for integrals now. So my first victim is going to be, I still have the 3, and I have x to the 8th over 8. Because just to remind you, that's the power rule, that it's x to the n plus 1 over n plus 1. And that's the integral of x to the n. And of course, plus c, but I don't care. I'll write the plus c, even though right now I'm not that. This is just a reminder of that rule. And we're going to use that rule for all three of these. Minus 15 times x to the 3/2, because 1/2 plus 1 is equal to 3/2, over 3/2. And I'm going to clean up this fraction as soon as we're done. As soon as I finish the next one. Plus 14 times, now this is a little tricky. You might think that 2 plus 1 is 3, but that's not 2, that's negative 2. So it's going to be actually x to the negative 1 over negative 1. And of course, I always have to write the plus c. Now I'm just going to clean this up a little bit. Although technically, like I said, if you don't clean it up, this is the correct answer. And I have to caution you, this is something that my daughter's when my daughter took AP Calculus, her teacher told her that if you get the correct answer but you don't simplify it, you'll still get full credit. If you get the correct answer but then simplify it, and then you make a mistake when you simplify it, they're going to ding points off you. So that's just something to be aware of. So I hope you understand the point of that story. The point of that story is that I'm bragging that my daughter took AP Calculus, because that's all parents do. They brag about their children. So here we go. Let's just clean this up a little bit. So this is just going to be 3x to the 8th over 8. Not much to clean up. Now this one here is going to be the 3/2. I bring it up to the other up top, so it becomes 2/3. Again, times x to the 3/2. I'm going to leave it that way. But the 3 and the 15 cancel. I get a 5. I'll clean up a little more. And this is just going to be minus 14 over x plus c. And then just to clean up a tiny bit more, 3x to the 8th over 8 minus 10 x to the 3/2. I'm going to leave it that way. Is it minus? I'm sorry. Yeah, minus, and this is minus 14 over x plus c. Now, I want to ask you a little question. If you notice, when the problem started, that was minus and that's plus. So I understand why this ended up as a minus, but why is that a minus? Did I make a mistake? Am I getting like, careless here? Or is there a reason why it's a minus? Well, there is a reason, and I want you to think about it for a minute. And then okay, time's up. The reason it's a minus here is because when I raise this power, it was x to the -2. I had to raise it to, the +1, so that's -1, and divide by, in other words, I had to raise it to the n+1 and divide by the n+1. So I was dividing by a negative. So this positive turned into a negative at that point. So that's what my final answer is: 3x to the 8th over 8 minus 10 x to the 3/2 minus 14 over x plus c. And that is how the professionals do that. Let's make sure you can see. Okay, there you go. Well, as I mentioned, there are some rules. I just want to. We've kind of been using them, but I want to, say them officially. So let's just go through them step by step, one by one. The constant multiple rule: the derivative of kf is k times the derivative of f. That's something we mentioned already. The derivative of a sum is equal to the sum of the derivatives, and these are things that we've actually used already. I'm just stating them in a formal way. The power rule for derivatives now. This is the power rule for derivatives, is that the derivative of x to the n is n times x to the n minus 1. That's something which we've used many, many times. And of course, if I just have the derivative of a constant, that's equal to 0, because really I could say that k is k times x to the 0, so it really fits into that rule. And the derivative of just plain x is 1, because x is equal to x to the 1 power. So that works out perfectly. The derivative of e to the x is just plain e to the x. And the derivative of a to the x is ln a times a to the x. Again, these are just rules we've done already in previous sections. And finally, the derivative of ln x is 1 over x. Now, why am I showing you these derivative rules? Because we're gonna now look at antiderivatives, and antiderivatives are just kind of, like I say, it's derivatives backwards. And a lot of the rules, there's a lot of the same rules kind of apply. Some apply exactly the same way, or some sort of a reverse way, but you'll see what I mean. So one is that if I have the integral of a constant times a function, that's equal to a constant times the integral of that function. We've actually used this without stating it so formally. We've actually used this many times already in the examples that we've done. The integral of a sum is equal to the sum of the integrals, or the difference, and we just like it works for derivatives, it works for integrals. So you see, A and B, what works for derivatives works for integrals. It's essentially the exact same rule. Now C is interesting. C is kind of the same rule. I mean, it is the same rule, but it's just going in the reverse direction. We're saying that the integral of x to the n is x to the n plus 1 over x to the n plus 1. And of course, you always have to add plus c. And the reason is because if I would, I mean, just think about it. If I would take the derivative of x to the n plus 1 over n plus 1, my n plus 1s would cancel out, and I would just get x to the n plane, and that would be the answer. Notice that n cannot be -1. The derivative of x to the -1 power, I'm sorry, the integral of x to the -1 power is not solvable with this power rule. It is solvable very easily with another thing that we learned. I don't know if I should even tell you what it is and spoil the fun, because I'm sure you want to wait to get down to the bottom of the page and see it for yourself. So let's continue. Anyway, the integral of a constant is just the constant times x. So the plus 2. And these are rules that we've actually kind of done this in practice. Now I'm just sort of stating them. By the way, this is my way. I like doing things, and I like doing examples and doing stuff in practice, and then kind of showing you, the rules as a sort of review of all the skills that we've been doing. The integral of e to the x dx is just e to the x. That makes sense, because the derivative of e to the x is e to the x, because the plus c, of course. The integral of a to the x is a to the x divided by ln a, not times ln a, but divided by ln a, because if I would take the derivative of a to the x over a to the x itself, I would get ln A times a to the x. The a to the x, the ln A on the bottom cancels the ln A on the top, and I'm just with a to the x. So it's kind of like off. It's just kind of going in the reverse direction. So where if before I had to multiply, now I have to divide. Before I had to, so on and so forth. Next, before I subtract, now I have to add, so on and so forth. And finally, the integral of one of x to the -1, which is the same thing as 1/x. That is the ln of x. And notice it says absolute value of x. That's because ln x is not defined for positive numbers. The domain of the log function is positive numbers only, not negatives. That's why it has to be absolute valuetized. Okay, well that's all I wanted to show you there. Now I want to jump back and do some more fabulous and wonderful examples. Let's look at this problem. The integral of e to the x plus 12 minus 16 over x dx. So again, notice there are no numbers. There's no limits of integration on top and bottom of the integral. So I'm looking. My answer is going to be a function. That's all it's going to be. The first. Well, I'm not even going to bother. Normally I would say, hey, let's rewrite this. You know, but we already. We already told you that the integral of 1/x is ln x. So let's just get right to it. So really, this is going to be a very straightforward problem. It's just going to be the integral of e to the x is e to the x. The integral of 12 is 12x. Why is that? Because the derivative of 12x would just be 12. The derivative of e to the x would just be e to the x. And the derivative of 1/x is ln x. So this is just going to be minus 16 ln x. And of course, plus c. And that's really my whole answer. That's it. We're done. That's the entire answer. And of course, the minus 16 is because of the minus and the 16. That's, So there we go. Okay, let's do another problem. Okay, so here we want to do is find f of x, capital F, notice it's capital F, such that f prime of x is equal to e to the x, and capital F of 0 is equal to 10. So if I'm saying that f prime is equal to e to the x, and they want us to find f, essentially they want us to take the antiderivative of e to the x. So if I have e to the x, I have the integral of e to the x. Again, there's no limits of integration here. It's just going to be equal to e to the x plus c. Now that's half the problem. That's half the problem. So we found f of x. So we did that part. And it's true that f prime is equal to e to the x. So we got that part. But now there's one more part we need. We want f of 0 to equal 10. Now here's my function. This is e to the x plus c. So in other words, just again, capital F of x is equal to e to the x plus c. I'm just sort of rewriting this. But if I would plug 0 in, I don't know. How do I know what this is going to equal? So what I have to do is I need to find a particular value of c, a specific value of c, to make it that when I plug in 0, I get 10. So all I'm going to do is I'm going to say f of 0 equals e to the 0 plus c, and that has to equal 10. And I'm going to use this to solve for c. So e to the 0 plus c equals 10. Well, what is e to the 0? E to the 0 is just 1. 1 plus c equals 10. Now I just subtract 1 from each side, and I get c equals 9. So my function f of x is equal to e to the x plus 9. And that's my final answer. So originally I had e to the x plus c. I didn't know what the value of c was, but once they told me that f of 0 had to equal 10, then the only way that was possible is if c was equal to 9. So again, this is kind of a two-part problem. The first part was finding the antiderivative, which in this case was super simple because e to the x is just e to the x. And that was part one of the problem. Then part two of the problem, and I needed to do part one first. Part two of the problem was taking my newfound indefinite integral and solving for c by plugging in these two values, 0 and 10. And that is that is how you do that. Let's look at another fun problem. I want to switch to the textbook for a second and show you something which I think is kind of interesting. That's straight in the textbook. And let me and then I'm gonna then we'll go solve a few more problems. But let me just share my screen for a second. So this is kind of cool. It's example 4, section 3.3 in the textbook. And they want you to evaluate the integral from 1 to 3 of x dx in two different ways. First, I want you to sketch a graph. Actually, just do a good old-fashioned geometry, as if you never ever heard of calculus. Then they want you to do it by finding the antiderivative. And then they want you to do it the calculus way. So first, I want you to do it the geometry way. Then I want you to do it the calculus way. So in geometry, the graph y equals x looks like this. It's a diagonal line at a 45-degree angle. And they want to find the area under this red, the curve. Now the curve happens to be a straight line, but a straight line, technically in math we call any line, even if it's a straight line, we call it a curve. And so we want to find the area under the curve, between 1 and 3 and between the x-axis. And here, this is simple enough. I mean, I can just count the boxes: 1, 2, 3, 3.5, 4. So the answer is just 4. And for those of you who are more sophisticated, you could also use the formula, because this is a trapezoid. You use the trapezoid formula, or as many ways you can figure this out. But just keep it simple. We see it's 4. It's very obvious that it's 4. On the other hand, we could do this with calculus. The integral of x is x squared over 2. And I'm going to plug in, and I'm going to put in 3 and put in 1. Those are my limits of integration. So I have 1/2 3 squared minus 1/2 1 squared gives me 9 halves minus 1/2, which is 8 halves, which is 4. So you see the answers are the same. Now that is so important. That is so important to that they be the same, because if they weren't the same, then something's wrong. Because if math is, you know what a very brilliant professor of mine once said, that what's special about math compared to other subjects in school is that in math everything is true. I don't know if you can say that about every other subject, but in math everything is true. And how can it be true if geometry is supposed to be true and calculus is supposed to be true? When geometry gives you an answer of 5 and calculus gives you an answer of 7, it doesn't make sense. If it's true, it should be consistent all throughout, and we see that it is. We see that we get the same answer whether we do it with geometry or we do it with calculus. The only caveat is that we have to do it correctly. No matter which way we do it, we have to do it correctly. The book makes an interesting point here, that the antiderivative of x is x squared, but isn't it also x squared plus 7? Wouldn't that also work? Because if I take the derivative here, the 7 just disappears. Well, look what happens here. If I do that, so I'm going to get x squared, 1/2 x squared plus 7, evaluated between 3 and 1. So I get 1/2 3 squared plus 7 minus 1/2 1 squared plus 7. And what happens is that the 7s just cancel out. And that's why we don't really bother. That's why when we do these definite integrals, we don't bother with the constant, because the constant is just going to cancel out. And we get 9 halves minus 1/2, which is 4. That's the same answer. That's just a nice point that the text is making. Okay, I'm going to go and do some more problems for you. Let me just find a nice good one for you. Okay, here's a problem. Again, it's from the textbook. It's kind of interesting. A program. A robot has been programmed so that when it starts to move, its velocity after t seconds will be 3t squared feet per second. That's the velocity. Okay. And we want to know, how far will the robot travel during its first 4 seconds of movement? Now, why is this even a calculus problem? Why not just do it with algebra? Rate distance equals rate times time. Well, the reason is because the rate keeps on changing. Every second, the rate, is different, because first it's it's t, it starts out at 0, then it's t times a half squared, t times 1 squared, t times 1.5 squared, t times it keeps on changing, and in this case, it's actually increasing its velocity as it goes. So you can't just say distance equals rate times time, because there is no one constant rate during those 4 seconds. It's constantly going at a different rate. It's actually it's increasing, but you know, so that's why we need calculus altogether. And B, how far will the robot travel during its next 4 seconds? So how far did it travel during the first 4 seconds, and then how far will it travel during the next 4 seconds? Well, this, my friends, involves calculus. So the distance during the first 4 seconds is going to be the area under the velocity graph from t equals 0 to t equals 4. In other words, it's going to be the definite integral. It's going to be the definite integral, the integral from 0 to 4 of 3t squared dt. And now, a very simple antiderivative of 3t squared is t to the third. So it's going to be t to the third evaluated between 4 and 0, which is 4 to the third power minus 0 to the third power, which is 64 feet. And here's the graph, and there we go. There's our function. The next part is how far is it going to go during the next 4 seconds? Well, guess what? We're just going to do the same exact integral, only we're just going to change the limits of integration. Instead of going from 0 to 4, guess what? We're going to go from, what do you say? That's right. We're going to go from 4 to 8. So again, I get the same t to the third power, and I get the same t to the third power, and between 4 and 8. So it's 8 to the third minus 4 to the third, which is 512 minus 64, which is 448 feet. And that is how we do that. Okay, let's take a look at another one. Suppose that t minutes after putting 1,000 bacteria on a Petri plate, the rate of growth of the population is 6t, not 60, but 6t bacteria per minute. So how many new bacteria are added to the population during the first 7 minutes? That's one question. And what is the total population after 7 minutes? And that is again a question that we're going to need calculus, because you can't just say distance equals rate times time, because the rate is increasing, the rate is changing. It's not the same rate. So so what are we going to need here? So the number of new bacteria, that's going to wind up being the area under the rate graph. So this is the graph, y equals 6t, because that's my 6t right there. And I basically want the area underneath that graph. So for part A, for the first 7 minutes, I want the integral from 0 to 7 of 6t dt, and that is going to be 3t squared. Now, why is it? I thought it was t squared over 2. What's going on here? Well, it is t squared over 2, but I have the 6 there. So 6 divided by 2 gives me 3. 3t squared, 0 to 7, which is 3 times 49 minus 0, which is 147. So that's how many new are added. And the new population, well, that's just going to be the old population plus the new bacteria. So the original population was 1,000. We started with 1,000 in the dish. We added, not we added, but 147, sprang up, and that gives a total of 1147. And that's the total. So 147 is what we got added on, and we need a calculus for that. And 1147, well, that was just addition. So good for that. I want to do one more problem for this section, and then we're gonna do one more problem, and then we're gonna end this video. Okay, a company determines their marginal cost for production. Well, we're going over doing bacteria and robots, and now we're doing marginal costs. A company determines their marginal cost for production in dollars per item is MC of X is equal to 4 over rad X plus 2. And this is when they produce X 1,000 items. So X is not just an item, X is 1,000 items. Find the cost of increasing production from 4,000 items to 5,000 items. So we want to find the cost of making that increase. So this is going to be a calculus problem. Again, it's always because things are changing. See, calculus is. I once I remember I once read that calculus is when things are changing. Algebra is when things are steady and constant, more or less, and calculus things are changing. Like in other words, what do I mean constant and steady? A person is running, but he's running at a constant rate. He's running at a constant speed, so you can figure out his distance because it's constant rate and so on and so forth. Once things start moving around and changing, that's when it starts to get more calculusy. Anyway, marginal cost, just remember that's the rate of change of cost. So the fundamental theorem tells us that the integral from a to b of mc of x dx, that's the same thing as the integral from a to b of c prime of x dx, because marginal cost is the change of cost. That's c prime means the change of cost. And that's just going to be cb minus ca. So so in other words, the integral of marginal cost is going to give us the net change in cost. And to find the cost of increasing production from 4,000 items to 5,000 items, we have to integrate the integral from 4 to 5 of mcx dx. And that's the integral they gave us, which was the again, we wrote it here in exponent form because with calculus it's always easier to use exponents. And now we just got to take this integral. So the integral is c of x, which is the integral of mc, is going to be 4x to the positive 1/2, because negative 1/2 plus 1 gives me positive 1/2. And I divide by that 1/2. And now the integral of 2 is 2x. Now, 4 divided by a half, not 4 times a half, but 4 divided by a half is 8. So it's 8 rad x plus 2x. Now I just have to plug in 5 and 4 and then subtract. So I'm just taking the integral. I'm taking 8 rad x plus 2x from 5 and 4. So it's 8 rad 5 plus 2 times 5 minus 8 rad 4 plus 2 times 4. And if you crunch all that in a calculator, you're going to get roughly 3.889. And that is my story, and I'm sticking to it. So it's going to cost $3.889 to increase production from 4,000 items to 5,000 items. Now, it may cost that much more, but hopefully you're going to make a bunch more. So that's of course we always hope for. Well, it's been a lovely video, and it's been wonderful sharing this nice time for you. And I will see you guys next time. Bye.